Alright, so I'm starting with some text up here. I want to talk about what the energy actually is. And we mentioned that the energy in the capacitor looks like this function, 1/2 the capacitance times the voltage squared. And if you take that voltage and turn it back into electric field, and you take the definitions of capacitance and you break everything up, you should get something that looks like epsilon naught times E squared. What I'm going to do is say this is divided by the volume. So I just realized this is energy density. So energy density. You're going to have a similar function for a coil. So for the coil, it's going to look like a function like this, but it's going to depend on the inductance of the coil and the current. And so if you solve through all this, you'll get the magnetic field squared over 2 times mu naught. Now, if I've made a mistake here, it's the derivation is very hand-wavy, but the gist of it is the energy in these things look like the square of the fields. All right, everything else, all the errors in here are going to be in the constants. And this is going to come back when we start talking about light. The energy in light is going to be in the electric and the magnetic fields. So I just wanted you to see that there is, energy in here and what it looks like in terms of the fields that we're dealing with. So when we discharge these things, so before what I showed you was the circuits where the battery was providing energy. But what happens if I just have a capacitor which has some V initial and a resistor? What happens then is essentially I start with the voltage as a function of time on the capacitor, and V naught is going to be Q naught over C. Right, so I'll have Q as a function of time over C minus, now the voltage here is I times R as the current flows around. So I of T times R. That's my Kirchhoff's law. But this I is really dq over dt. So that lets us solve things nice and neat. And what we end up with is the charge, the function of time, is some initial charge that's built up on here. And we can call it what it is. It's C times V naught. And then we'll have e to the minus t over RC. Now, you'll notice this turns up. The reason we have it look like this is because when you put numbers that have units in an exponential function or a logarithmic function or any sort of trig function, the units have to go away. All these trig functions are defined as unitless things. We don't know what the sine of a meter is or what the exponential function for 12 newtons is. All the units have to go away. So R times C shares the units of time. And the idea is this R times C, we can define a time constant so I'm going to write what it sounds like. I want to draw it. It's a Greek letter T, tau. And that's going to equal R times C. And what it means is it's the time for, in this graph, as this thing discharges. So we'll start at some initial value, Q naught. It's the time that it takes. If I pick this point out as that particular time, it's going to be Q naught over E. It's time for where this function equals e to the minus 1, which is about 0.63. That's one time constant. Now what happens is there's another point over here. This point is Q over E squared. And it is from here to here 2 time constants. So what happens is the time constant is the time that it takes to lose 1 over E. Time it takes to reach 1 over E of its original value. When we do this in the labs, and you didn't get to do this year, we ballpark it. Is essentially Q over E is very nearly Q over 3. And so we say, well, how long does it take to get to 1/3 of its value? And the reason is actual capacitors take a long time to build right. And no one builds them to a high accuracy. So the value that's printed on them, we don't know how accurate it is. It's like 20% off. So Q over 3 is just fine. But that's the technical outcome, is this constant, RC, is the decay constant for this function. Right. Now, the other thing that we have is a coil, and the coil's energized. What happens there? Well, we're going to have something else that looks very similar. And the idea is we're going to have a time constant here that has to be a time. It has to be something in seconds. And it has to have the correct units. And the correct units are going to be R over L eventually. But what we're going to do is start with a resistor and a coil. This is what's called an RL circuit, right? And we're just going to let it discharge. And what happens is the current flows, because what's happening is as the field decreases, the coil will try to make a new current to replace it, trying to maintain the field here. And so instead of it going all down at once, I decays just like that. And effectively what we have over here, the voltage is I times R. Over here is L di dt. And that means I is some initial value, right? So it depends on what the EMF is, what the voltage is on the coil, divided by the resistance. That's your initial value. E to the minus R over L T. Right. Now, I don't want to get so deep into this that there's just massive amounts of electrical engineering. This is baby's first electrical engineering. But there is a little bit that you need to know on this stuff. Note in the homework that what I told you was all about RC circuits, resistor capacitor circuits, and about transformers. So I'm not worried a huge amount about this. But you should know it if this is the field you're going into. You need to not be surprised by going from this step to this step. And then if you want to know how to do that, that's not too horrible. The idea is that these things are pretty straightforward. Get the L on one side. di over dt is R over L times I. And then you integrate both sides. And then you integrate this thing. We got to have I on this side. So we'll have log of I is R over LT. And then you convert it to that form. So if you want to solve these things, it looks like we haven't done anything that you understand, but this is the stuff we were doing in kinematics. How do we get to kinematic equations? Start with a differential equation, and we integrate it. And that's what we did here. And that's what we do in these others, except they suck. So we're kind of letting it be. I do have one more thing to show. I'm going to keep doing it. This video is getting long, but it's supplemental anyway. What happens if we just have a coil and a charged capacitor? Right, so we'll do that circuit. This is what's called an LC circuit. And it is a capacitor with the initial on it, so it has charge already on it. And I want to talk through this in steps for a minute. What's going to happen is, the moment this thing's connected up, current's going to try to flow this way to discharge a capacitor. And that means you suddenly get a magnetic field through the coil. Now that magnetic field induces a new current in this coil. And due to Lenz's law, it's got to undo the field that showed up in the first place. It's got to undo that flux, which means you have a back current or counter current flowing backwards. What that counter current does is recharge a capacitor. And so if we look at the voltage, right, so V and T, it should look like this. What happens is, as the voltage drops, as it dumps charge into the coil will eventually pick up field, and then coil will discharge back into the capacitor and it'll oscillate. So we can do Kirchhoff's voltage law on this circuit. All right, V naught is going to be Q over C. So the voltage here is going to be Q as a function of time over C. It's going to be the EMF in the coil, which is going to be L di dt, which is a function of time. And remember, we also have I is dq over dt. So this is going to be L d over dt dq over dt. So we're eventually going to get a function that looks like d squared q over dt squared is q over, as a function of time, over LC. This is a sinusoidal differential equation, and it has a natural solution. Is q of t is some initial charge cosine omega t plus some phase constant for the sine function. And it's going to look like this. But the idea is that this angular frequency so if you remember waves, we talked about angular frequency. That's going to be 1 over square root LC. I know it seems like I'm pulling stuff out of the mess. The idea is that you take this thing, you do 2 derivatives of it, and you will get that thing with minus sign possibly. Have I dropped a minus sign somewhere? Yeah, I have. So this we can convert into the actual frequency, and for brevity I'll just write it down here. F is 1 over 2 pi square root LC. So what this means is if you have a coil and a capacitor and have some energy stored in them, they will naturally oscillate. Is that they will trade based on the discharge current of the capacitor and the back EMF of the coil. They will trade current back and forth, and they will charge and discharge each other and follow this sine wave. Now, the problem is real circuits down here also have a little bit of resistance. And so on this curve, what we end up with is more of a decaying sine function. But you can get around that. What you do is you put something in here that amplifies your signal. You have to get an amplifier. So what that means is we've just described how a lot of your electronics that transmit and receive signals, how they work. They work through some sort of resonant structure that has a frequency where it holds a lot of energy and transports it, its natural frequency, and some sort of amplification. Okay. So this is the design of all sorts of transmitters and receivers, is at the basics some sort of what's called a tank circuit, an LC circuit, that encourages oscillation and some way of keeping the energy, of continuing to provide energy to the circuit. Yeah, this went too long. So, very little of this do you need. If you watch the RC circuit stuff, that's enough. But if you're interested in this stuff, you absolutely should see this stuff. Especially if you're going to do electrical engineering or even other engineering. You'll probably have to take a class that involves how this stuff works at some point. So it's worth it that you at least see it and understand, hey, what's going on here is differential equations, and it's how currents change over time. So just understand is you might be completely confused, but I really have tried to cut it down to the basic stuff. There's more. We could go, like, what happens when you start varying the current that's applied by some voltage source that's not these? What happens to a capacitor that sees a varying source, or an inductor that sees a varying source? So, yeah, there's more stuff. It's okay. Relax. Next time should be when we start talking about light. I hope. We'll see.